Okay. Greetings to everyone. Thanks again for this opportunity. So let me briefly introduce myself and the topic of my brief talk. As Christian said, my name is Mattia and I'm working in the Carbon Group hosted by Polytecnico of Torino. I'm a postdoc research. These are the other members of my research unit, the head of the group, Prof. Alberto Tagliaferro, the other two scientists, Mauro Giorcelli and Pravin Jagdale, and our Raman specialist, Massimo Rovere. As Carbon Group, our vision, our mission is explore all the possibility related to carbon material. This choice was related when the Carbon Group started this activity to the main and great role that carbon plays in our society since the first discovery in the early 20th century of synthetic polymers. Our activity started in 2005 with the study of several kinds of carbons, but today I'm going to summarize why we approach the biochar and how biochar could be used for the production of composite materials with enhanced mechanical and electrical properties. Firstly, composites. Composites represent a huge marketplace. That is, value is around billions of US dollars, even if with the actual crisis. Among all of the composites material, polymeric-based ones represent up to 70% of all of them. Among them, carbon-based ones are the most relevant. So we start to study them, but we start from far. Our first studies were about very fancy fillers, such as carbon nanotubes, graphene, fullerenes. Those materials showed amazing electrical, mechanical properties, and they are great for electrochemical and optical applications. But they have a very high cost. We are talking about hundreds of euros per gram. We are talking about hundreds of euros for square centimeter for real graphene. And the production of these very high-tech materials is quite complex, and it cannot meet the requirements for the large-scale production in most cases with acceptable qualities and quantities. So when we started to move around, search for investors, and talk with companies about our good results with carbon nanotubes and other materials, they say to us, okay, but carbon composite field is different. And we found that carbon composite field is dominated by another material, carbon black. Carbon black is the fielder. When we are talking about composite that contain carbons, the first material that everyone used is carbon black because it's cheap, because it's largely produced, because it can be tuned for enhance selectively the electrical properties. The main drawback of carbon black is represented by its nature. It is produced from oil residues, so the environmental impact is quite high. So we moved on. We searched for something different, something more sustainable, but something that can match the high properties of carbon nanotubes and graphene and such those materials with the price of carbon black and a lesser carbon footprint. So we start to work on biochar, that all of you knows that is cheap. It could be produced from renewable sources and waste streams, and could be tuned for enhanced selectively the electronic properties. We found, of course, that there are some unresolved problems in this case. For example, the lack of commodities that producing biochar in every country, and more important, a lack of information and a lack of nexus between biochar producer and material scientists. So we start to work on biochar, and our first question was, can biochar replace CNTs in high-tech composites? So we start to evaluate the effect of biochar in CNTs in epoxy resins. As you can see from the stress strain curves here, biochar, even if in higher concentration, can outperform CNTs from a mechanical point of view, increasing the Young modulus, increasing the elongation at failure of the composites. And this was due to the particular crack propagation inside the composite. So the first question was answered, and the answer is, okay, biochar can emulate CNTs from the mechanical point of view. At this point, a lot of questions arose. Firstly, if we change feedstock, we are able to change the properties of the composites. So we use different biochars using several kinds of feedstocks. Here you can see results regarding biochar used for enhancing mechanical properties of epoxy resin produced from wheat straw and miscanthus. And as you can see, different biochars induce different properties. We found that this was due mainly to different things. The first one was related to the fact that different feedstock lead to the production of different biochar with different grindability, and different grindability leads to different particle size distribution. Particle size distribution is the first parameter that affects the mechanical properties. The second one is more related to the roughness of the biochar particles surface. So smooth surfaces induce greater elongations, as in the case of miscanthus. Rougher surface, like in the case of wheat straw, induce brittleness with an enhance of ultimate tensile strength and Young modulus. More important, here you can see that biochar-based composites can outperform carbon black ones. So biochar could be used as a sound replace for high-tech fillers, but also for carbon black. A further step was evaluate the influence on shape of biochar particles on the mechanical properties. So we chose round-shaped particles produced from cellulose nanocrystals and carbonized them on the left corner of the screen, and rod-like particles on the right. So we found that there are differences in between, because waste cotton fibers after carbonization in high concentration inside the epoxy create a network that reduces the elongation. So also the shape of biochar particles affect the properties of the composite. Finally, we check the effect of pyrolysis temperature and heating rate. Those are the main parameters that could be faced during the biochar production, because they are very important for the whole pyrolytic process. And we found that heating rate is not so important, but the highest treatment temperature used for the production of biochar is a key parameter and could be used to shift from a brittle material to a ductile one. But those results could be shifted from thermoset composites like epoxy, the one that you saw here, to thermoplastic ones. This is the first pioneeristic work published from Bhattacharya group on polypropylene. And you can see that tensile strength and tensile modulus could be enhanced by all the biochar that you use to produce the composite, but in this case, the elongation decrease, appreciably decrease. And this is very common for thermoplastic materials. The addition of biochar in this case generally induce a brittleness in the composite. But for thermoplastic, is also important the way of production. We test several of them. Here you can see melt mixing and some melt casting results. In this case, by using PLA and West coffee derived biochar, the picture on the right, you can see the mechanical properties are not so enhanced by the addition of biochar, but the thermal stability is greatly enhanced. And this is very important for an application that you will see in the next slides. But mechanical properties are not the only target when you produce a composite based on carbon materials. The other relevant properties is related to the electrical conductivity of composites. And in this case, the story is a little bit tricky for biochar, because the electrical conductivity of biochar is strongly related to the temperature used to produce it. A good conductivity could be achieved for temperature up to 800 degrees. And this kind of temperatures for the processes require an investment in energy and cost. And we are looking all around if this investment in terms of energy and cost could be counterbalanced by the properties. And the properties of biochar at higher temperature are very interesting. On the right of the screen, you can see the evolution of biochar monitoring by Raman spectroscopy. Here there is a particular way to approaching Raman of disordered material that we developed for the analysis of biochar. But you can see that higher temperature, biochar became more graphitic, even if it is a non-graphitizable carbon type material. But, as in the case of mechanical properties, we compare biochar with CNTs by using mainly two different approaches, one in DC current and one in AC current, to evaluate everything that we can check. So, but before this, we confirm that temperature is relevant for conductivity. And even if an increase of 100 degrees is in the during the production of biochar induce a very different conductivity in the final material, as you can see here for miscanthus. So CNTs and biochar for composite containing carbon materials. As you can see, CNTs in the concentration of 2 and 4% displayed a good conductivity in the composites. Nonetheless, biochar in higher concentration, up 20%, can outperform, at least at higher frequencies, the results obtained with CNTs. And this was due to the different distribution of carbon particles inside the polymeric matrix. CNTs display the tendency to create agglomerates, while biochar is very easily dispersible in all polymeric matrix. But a further step was the comparison between biochar and carbon black, and also in this case, you can see that only biochar composites display a good conductivity in these measurements, even if neat, pristine carbon black has a native conductivity higher than the biochar used in this case, tea leaves treated at 1000 degrees. That in this case, it's a quite high temperature, but as you can see from the graph on the left, in this case, biochar show a conductive behavior close to a metal. The reason that lay behind this phenomenon are practically due to the dispersion of the material inside the polymeric matrix, and it is quite appreciable in this case. Here you can see different dispersion inside the inside an epoxy matrix of carbon black and biochar. In the case of carbon black, you can see some island of filler inside the composite, while biochar from coffee is well dispersed. This dispersion lead to the conductivity values that you can see on the left. So biochar could be used to replace both high-tech fillers and commercial one for the production of conductive composites. This is the other achievement of our research. For these studies, we came to the applications. Firstly, biochar could be used as toughening agents for fibers-based composites. As Mattikiewicz showed for carbon fibers, the addition of very small amount of biochar could enhance storage modulus, decreasing the brittleness of the composites. Similarly, fatigue tests that we did for agave fibers composite after the addition of 2% of biochar show a great enhancement of durability of this kind of composites. And this is one of the great goals of the use of biochar for these materials, the durability. So the increased life of all the materials based on biochar is a quite strong point. As I told you before, biochar enhanced the thermal stability of the matrices and could be used to improve the flammability resistance by direct mixing with the polymeric matrix, on the left the case of polypropylene, or by simply coating, as in the case of knit fabrics on the left. But these materials could be used also for very high-tech applications. We developed humidity sensors based on biochar. Humidity sensors that could be reversible and then could be used in a very effective and productive way in different humidity percentage, but could be also used for electronic devices development. Recently, we published a work about the first production of a device that you can see on the right, based on high thermal treated biochar inserted into a silicon matrix for the production of piezoresistive material. So, from common composites applications like enhancing the mechanical properties of the electrical properties, we can reach real field application with high costs. So, in conclusion, the point that should be taken account for the production of biochar-based composite is the thing that a groundbreaking event that can spread the biochar use far from the soil applications or water purification is missed. Scientific communities is a little bit skeptic about bio-derived carbon or simply a biochar from pyrolysis as a replacement of high-tech fillers. But there is space for new application, there is space for innovation. So the use of biochar as filler for composites could be a very strong advance for the spreading of using of biochar far away from the current state of the art. I can understand it's a little bit difficult, and it's a field that requires a lot of multidisciplinary approaches. So after years and years, we wrote also a book about this for providing a general overview about what we can do with biochar in a very advanced fields. And we firmly believe that biochar could represent a game-changing material for carbon scientists, a material that can lead the transition between a society that's more accountable for carbon footprint and sustainability. With this, I finish my presentation. I thank you for your time, and if there, I'm ready for take your questions.
Thank you very much, Mattia. Very nice presentation and a very nice overview in a field that probably not all of us are so familiar with. So for the audience now, if you have any questions, please write them in the chat on the right or at the bottom of your screen. There should be a button with chat. Or otherwise, you can just unmute yourself and ask Mattia directly. So I would have a question about how advanced is your biochar production? Like how important is homogeneity of your biochar to be used in a composite?
For answer to this question, I need to clarify the final use. For example, homogeneity is essential for mechanical properties, because if I suggest to an investors or another research to use a biochar for enhanced mechanical properties, I must be sure that the biochar is the same time after time. So homogeneity in this case is critical. For electrical properties, it's a little bit different because I can use also mixed feedstocks, and I don't care about the homogeneity of the sample. I care about homogeneity of the properties. So in that case, what I need to be constant is surface area and conductivity. So this answer should be split in two. One for mechanical aims, and in that case, the reproducibility is the first and main thing, and the other is for electrical. For electrical properties, I need only reproducibility in properties. So I need generally, if the production process is stable and well established, is better because it's far simpler. But more for enhance the conductivity of composite, we saw that few processes use temperature higher enough for that. So we need an ad hoc process, and in that case, the standardization is a little bit lesser. That's my general opinion about.
Okay, thank you. So you still have time? Yeah, so here we have a question. Let me read that out. Did you try to communicate with manufacturers with your findings? And if yes, what was their feedback?
We did. They were quite interesting, and we are working on that. We are searching for opportunities to translate our findings to a real business, but we are a research group, so we can just serve as input makers. We cannot make a business of our research as it is. But yes, for the producer that we talked with, they were quite interesting. So, as I said, there is space for those things.
There was a second question from Terra Bretta Developments. Have you ever considered using estuary silt material?
No, not yet, but probably could be a good chance for at least one of the applications that I show in the presentation for the flammability, because what we found is that a good concentration in inorganics could be positive for that kind of application, but we didn't consider it till now. So we are hoping for a suggestion and possible collaborations.
And another one from Reinke. Did you only consider pure biomass, or did you also investigate pre-treated biomass, so doped ones?
Okay. We did all of these things. We generally use pure biomass as it is for several reasons. For example, for CNCs and cellulose, for the shape factors, the aim of that study was just check a particular aspect, so we didn't pre-treat them. But we are also working on tailoring the surface of biochar by pretreatment biomasses with metallic salts or through acidic development or acidic hydrolysis. For example, we have open research activity about the production of energy storage systems. In that case, for the production of biochar, more effective biochar, let's say, we are also evaluating pretreatments.
Okay, thank you, Mattia. So we still have 1 or 2 minutes for another question. So if you have one, type it fast, please. Or better, even just unmute yourself and ask directly.
Yes, Benjamin Reinke again. Thanks for your answer just before. One question that I have with the examination, or with your, let's say, with measuring electrical conductivity for not for solutions, right? So you took it, you had parts made. Is there any standard for that? Because we're struggling a bit to find any common norms to measure those.
No.
So it's more or less. And what did you take as a reference then? Because I guess that's what's needed then, right? Some kind of reference.
The first reference that we used was a work by Gia, published in 2018, but my memory is not such strong in that case. They developed this method for measuring the conductivity of carbon monoliths, and we adapted it.
Okay.
Generally, if you want to have a standard approach for this kind of measurements, the 4-probe methods is the best. But in the case of biochar, it's practically useless because the particles are particles, so you cannot use it. That's the main problem. If you want something more standard, I can suggest you an electrochemical approach. Make an ink and measure the conductivity with electrochemical systems. It's a little bit more complex, but it's quite effective. This could be a solid reproducibility approach. Otherwise, we are working with another research group in Polytecnico for develop an approach to evaluate the conductivity of particles inside the composite through AC measurements, but we are still working on it.
All right, thank you very much.
Great. And last question from Steve Harrison for you. You considered heating rate and temperature, but did residence time had any effect on the result?
We didn't consider it in the study that I present because when the pyrolysis ended, I cooled down the reactor very fast. There is a paper about this published by our research group in collaboration with the University of Toronto. And in that case, we also considered the residence time of the materials inside the oven. In that case, it was a little bit different because the residence time was long, let's say in this way. But yes, we consider it also.